is performance validation using PSS. Here, the abstract. There are so many challenges in the post-silicon validation, and these challenges are not getting any easier to do the increase in the complexity of the modern SoC designs. One aspect of this is the increase in number of embedded process cores in SoC, as well as the firmware content needed a proper operation of the design. Therefore, putting more demands on the time and resources required to create efficient embedded software as opposed to silicon performance validation effect. The embedded test software will need to verify the proper operation and codification, synchronization, and performance of the processor subsystem, and the memory subsystem, and the I/O subsystem in the design. In this paper, we will discuss challenge of verifying multiple versions of our test chip implemented using the advanced design implementation methodology, exploring cell libraries, on-chip monitoring IPS, new physical implementation techniques, how we used the portable test, and a stimulus standard PSS in addressing this challenge. We will also discussing the lessons from this project, the advantage of using PSS, and the possible future enhancement. Introduction. New semiconductor technologies and design methodology improvement needs to be proven in the test chip before mass production. These improvements consist of the library cells and on-chip monitor IPs and newly developed physical implementation technique to advance performance and power consumption in SoC design. The test chip is fabrication and used as vehicle for evaluating the effectiveness of the new technologies and design methodologies. The information collected through the test chip is used to improve our semiconductor technologies and new methodology continuously, and the technology and design methodology continuously, and to help our customers with making the design trade-offs to selecting the technologies used to implement their designs. Figure 1 shows the architecture of our test chip. There are 5 CPU blocks in the design: BAK_CPU02, BAK_CPU4, and each CPU blocks had quadcores. And a new design methodology are implemented on the CPU blocks, and the improvement in terms of power and performance area (PPA) are measured by the defective CPU benchmark programs and long-running stress tests. Each CPU block is implemented using the different cell libraries and physical implementation techniques to support different set of the requirements. Since this chip is built on a platform and the number of CPU blocks can easily be extended, and a system IP like CPU and PMU can also be adjusted automatically. Figure 1 is test chip's block diagram. The verification requirement and solutions. One of the goals of our test chip is to use it as the vehicle of the evaluated performance and power consumption of targeted design methodology. This requires us to create test scenarios that can be adapted to the different configuration as well as different implementation of the test chip. To simplify this task, we decided to use PSS and Perspec to create reusable test scenarios and let the tools handle the randomization, resource allocation, and synchronization, and accuracy code generation. In the remaining of the sections of this paper, we will give more detailed description of our test scenarios and sample PSS implementation of these scenarios. We will also discuss our experience with using PSS and our estimate of the improvement in productivity as compared to the manual coding. Finally, we will discuss the lessons learned and how can we incorporate more PSS in our post-silicon performance validation effort for future projects. Section 2 is the approach and implementation. We follow the 4 steps approach for performance validation of our test chip using PSS. A. The creating test scenarios to measure the performance. It is important to have the suitable test scenarios targeting the difference of the CPU block. The implementation details like STA, static timing analysis, timing report are used to determine the clock speed and the maximum bandwidth, and when generating a test scenarios. A traffic profile generator, TGB, is developed using PSS, generates intended test scenarios easily. B. Creating a de facto standard benchmark test. Dry student core mark and LM bench are widely used CPU benchmark programs for performance. GZIP has frequently been used for measuring the performance of monitoring IPs. These benchmarking programs have been implemented in PSS as part of the tool library. This simplified the task of incorporating these programs in our performance test suite. The performance differences due to the differences in the design methodology can be recognized clearly with the incredible benchmark test. The synthesizing long-running test scenarios. Since the performance measurement will be measured on PCB board, the test scenarios need to be sufficiently long. They can be synthesized by combining the simple and shorter tests in our testing plan. These scenarios are also put in runtime loops to further increase the test duration. D. Automated and reusable PSS environment. In the future version of our test chip, the number of CPU blocks will vary depending on the requirement. The current PSS environment is designed to be reusable without any modification. The following section describes how these test scenarios are implemented in PSS for our current test chip. Table 1 and Table 2 show the processor and memory configuration of our test chip. As of Table 1, a processor configuration of current version of test chip, and Table 2 is memory configuration of current version of test chip. A. The test scenarios meant to measure performance. The measured memory read-write performance from the CPU clusters, and we created memory traffic profile TF scenarios that have one or more cores accessing the memory concurrently. Some of these key parameters we want to vary for these scenarios are: number of process cores to participate in the test, direction read only, write only the random selection, bandwidth in megabyte per sec, number of transactions. The memory TP scenarios can be broken down into simpler sub-scenarios. Each sub-scenario has exactly one process core performing memory access. The sub-scenario is implemented as a PSS action. And a SML traffic profile action with the following controls knob. Process core to execute this action. Direction, read only, write only, random selection. Bandwidth in megabyte per sec. Number of transactions. Note that we have the base specific profile action SML traffic profile. We can implement our memory TP scenario. The figure 2 shows the PSS code the memory TP scenario. This is the figure 3 is the memory TP scenario. 3 and a multi-core SML TP scenarios allow the test writer to select a number of the process core to execute SML traffic scenario profile action in parallel. As you can see from the PSS code of our memory TP scenarios in figure 3, and the multi-core SML TP action has the following the control knob shown in the bolded font in the code. The procedure subset. This data structure consists of the multiple control knobs. These control knobs allows the test writer to select one or more process cores to be used for these scenarios. Direction. Specify the memory read or write transactions. MPBS. Specify the bandwidth in the megabyte per second. Number of transactions. Specify the number of read and write transactions. Note that the procedure subset control knob is type SML procedure subset select underscore S, which consists of the following key control knobs. Intersite, how many cores, 1 to 10, 1 to 24 our chip. Bool, whether 0 is in. Bool E2, whether E3 is selected or not. Selected, a list of contains the cores selected by the test writer through our control block, control knobs. And int num is a 0 to 4, number of cores in the cluster 4, cluster CL4. Note that these control knobs can be created automatically from the table 1. by PSS tools. This is how to tie the SML procedure subset select S was created by the PSS tool. Using these control knobs, the test writer can easily specify memory-specific profile for different CPU clusters. Figure 4 and 5 shows how the test writer can constrain the memory TP scenarios for cluster 0 and cluster 4. And figure 4 is the memory TP scenarios for cluster 0. Figure 5 is the memory TP scenarios for cluster 4. The figure 6 shows the one of the tests generated by the memory TP scenarios specified in figure 5. All 4 cores in the CL4 is E0 to EJ3 are 1, 2, 3 are performing a memory write operation at a rate of the 800 megabytes per sec. The profile underscores the delay action in the UML. The diagram determined of the delay between the write operation so that the specified rate is achieved. The loop over 12 will specify the value of the number of transactions in the TP underscore C14 action. The figure 6 is one of the tests generated for the test TP scenario specified in figure 5. The B, standard benchmark test. Performance for each CPU cluster should be measured individually to evaluate the effectiveness of the technology and methodology used to implement that particular CPU cluster. It is also useful and a credible way to use the de facto standard benchmark test to measure the performance index. We selected four standard benchmark tests for our project: Drystone, Cormac, LM-Bench, and Juju. Drystone and Cormac are good measurement of the general purpose CPU performance. LM-Bench is provided a good measurement of the memory bandwidth in the latency performance, and Juju benchmark can figure out the efficiency of both CPU and memory system. To use these benchmarks in the PSS scenarios, we wrapped the open source code in PSS action. Key attributes of these benchmarks, such as a process core and memory block, and etc., are provided as a control knob of these actions. This simplifies the task of creating the benchmark test for multiple process cores and different memory configuration. The benchmark can also be combined with the other test scenarios, and such as DMA scenarios, and to evaluate the performance of the CPU cluster when there are other system activities. To measure the performance, we also created two other actions. Start PM counter. This action resets the ARM performance monitors cycle counter register CMC CNTR and enables it to start counting. The stop PM counter. This action stops the ARM performance monitor cycle counting register and return it the correct value. The figure 7 it shows the PSS. Figure 7 the Cormac scenarios. PSS is coded for a simple benchmark scenarios. Figure 7, the Cormac underbar scenario starts with the resetting and enabling the ARM-PN, CNTR, and it runs the Cormac. When the Cormac is done, it stops the PMC, CNTR, and gets the total cycle for this test. And the Cormac action can be Cormac action will be replaced with other benchmark action to a different benchmark. A more complex PSS scenarios can be written to allow the test writer to select which of the benchmark action to execute or to combine the benchmark actions with other system traffic. The C, long running test scenario. One of the main purposes of post-silicon validation is to check the design correctness. Whether the design meets intent or not, it needs to be done. With a real use case scenarios on PCB board, traditionally, these use case scenarios were created manually, and they usually didn't have a very good coverage. In order to improve on this, we leverage PSS to generate more tests and to get better coverage using randomization automation provided by the PSS tool. For post-silicon validation, we can run much longer tests, and these long-running test scenarios are preferred because they can cover hidden bugs that are not detectable with a short test. Our test chips provided a complete system connectivity among the interconnected memories of system LPDDR4, internal RAM, ROM, and the multi-port prefers such as UART and I2C and SPI and the QSPIs while running the CPU workload. To check the system connectivity thoroughly, we need to activate as many hardware resources as possible at the same time. This helps us to find corner case problems as well as measure our consumption. Figure as shows the block diagram describing the design connectivity. For example, DMA0 moves data from the LPDDR4 to UART24 display, and DMA1 moves data from the QSPI to LPDDR4 reading storage data, while CPU is performing algorithms via SRAM and LPDDR4. The figure 8 test chip system connectivity data paths. The challenge of creating these long-running test scenarios with multiple bus masters running concurrently is to resolve the resource conflict, memory allocation, interproposal communication, and synchronization. In addition, in order to facilitate the creation of long-running and meaningful tests, we also need a way to compose more complex scenarios from the simpler scenarios. Using PSS, many of these issues were handled automatically for us. As a result, we can generate corresponding long-running tests easily and extend it to a new test scenarios quickly. The figure 9 shows the PSS code for a DMA and memory traffic scenarios. In this DMA underscore PTP scenario, the test writer can select processor cluster to run test. The constraint not shown in the brevity in this scenario will ensure only the cores the specified cluster are used to execute this scenario. In this case, one of the cores will be used to execute the following instruction. Start on the PM counter, DMA scenario, stop PM counter. The other 3 cores are used to execute memory TP scenario, multiple SML TP. Note that the DMA TP scenario is constructed from the simpler scenario actions that we developed and discussed in the previous sections. This is figure 9 DMA and memory TP scenarios. The figure 10 shows the PSS code for a DMA TP scenario running the cluster CL0, and figure 11 shows the UML diagram for one of the generated tests for this scenario. Figure 10 is running DMA underscore TP scenario on cluster CL0. And this is the figure 11 is the UML diagram of the DMA TP test cluster CL0. The sample C code generation. The UML figure 11 shows that 4 cores are used for this scenario. Note that they are implicit synchronization point shown in this diagram. The sync point 1. At the beginning of the test, cores A1, A2, A3 have to wait for A0 to complete the execution of the start PM and counter action before they can execute the first write data action. Sync point 2. At the end of the test, core A0 has to wait for core 1, A1, A2, A3 to complete the execution of their TP scenario, which consists of the executing a sequence of write data profile delay in a loop over the 16 times before it can execute the stop PM and counter action. The figure 12 shows the code of snippets for core A0. Figure 13 shows the code snippets for core A1, and the IPC interprocess communication message for 2 sync points are annotated in the code. The figure 12, the 2 sync points are line 1063. Core A0 send the IPC messages to core A1, A2, A3, Once receiving this message, these cores will start executing their scenarios. Lines 1094 and 1001 and 01. Core A0 is waiting for core A1 to complete. After A0 will need to wait for A2 and A3 and complete range 1102 and 1117. This code is not shown in the figure 12. Once cores A1, A2, A3 finish executing their scenarios, core A0 will execute the code of stop PM and counter as action lines 1118 and 1125. In figure 13, the code for the first sync point are lines 1023 and 1030. The code for the second sync point is 91042. This is sync point 1 of the sync point 2, and in figure 12, generated C code for A0, DMA underscore TP test score CL0. And this is the figure 13 and generated C code for core A1 and a sync point 1 and a sync point 2, these figure 13. As you can see from the code snippet of figure 12 and 13, our PS tool handled all the IPC and synchronization automatically. We did not have to worry about any detail related to C code generation. Using C as PSS, our productivity increased significantly since most of the time we worked at the action level. We designed, analyzed, and debugged our test scenarios at the action level using the UML diagrams and the debug tools provided by Perspec. If a test failed, we could isolate these issues to a certain action quickly by reviewing the test progress messages. Once the failed action was identified, the next step was to review the generated C code for that action. This was the only time that we needed to work at the C level. So post-silicon test. For post-silicon test, we want to create a very long learning test. We use the PSS repeat statement to execute the scenarios that we used the simulation multiple times. Figure 14 shows the PSS code for post-silicon scenarios that run the DMA and the memory TP scenarios on a specific process clusters. Figure 15 shows the UML diagram of one of the tests for this scenario learning cluster 0. Note that figure 15 in a PSS repeat statement generates scenarios that repeatedly execute the DMA underscore TP scenarios 9,999 times the outer loop. And the first 14, the figure 14, post-silicon DMA and the memory TP scenarios. And this is the figure 15 post-silicon UML diagram of DMA and the memory TP test on cluster CL0. D. Reuse of the PSS environment and scenarios. It is redundant work to develop the PSS environment every time that a test chip changes. We need to consider the reusability for future projects while developing current PSS environment. The several component will changes in the next version of our test chip, such as the number of CPU clusters or number of DMA and prefers. Memory configuration can also vary. Therefore, all project-dependent configuration are put in a configuration file written in CSV file format, and this configuration file is organized as tables, comma-separated value. The content is project-independent information of the test chip. Some typical configuration tables are process table, a memory table, page table, etc. Table 1 and 2 show the type of information contained in the process configuration table and the memory configuration table. The PSS tool, Perspec in our case, reads the configuration file and automatically generates the PSS model of the processor and the memory subsystems. This model consists of the common data types, control knobs, data structure to represent the state of the system, help functions to access the model primitives and their status. To create an reusable PSS atomic actions and scenarios, that is a compound action, we don't refer to project-specific attribute. We use the common data types, buffers, and control knobs generated from the configuration file. For example, in the DMA-TP scenarios in Figure 10, we use the following data type, SML cluster tag E and SML processor tag E. These data types are generated by the PSS tools from the table 1. The values of SML clusters tag E for the current version of the test chip, CL0, CL1, CL2, CL3 for the next version of the test chip where we might have the 10 clusters and the cluster names might change to C0 to C9. Since the DMA-TP scenario does not refer to any of the cluster name, it can still be reused in this new design. We get setting up the environment for the new design. The only thing to change in the configuration file, by changing this information, we can easily reuse the environment in PSS scenarios and most of the tests that are referred to specify the project attribute such as DMA_TP_C L0 action in figure 11 will need to be rewritten. The results. Figure 16 shows the performance result of the Samsung design methodology DM measured by the PSS scenarios. BLK_CPU 0 is the normal block where the traditional Samsung DM is used. BLK_CPU 1 and CPU 2 are blocks where newly developed Samsung DM is applied to a top of the BLK CPU 0. The new Samsung DM shows a 4 to 9% performance enhancement measured by the PSS test scenario consists of the de facto CPU benchmark test and newly developed traffic profile generator. The traffic profile generator has a big advantage on injecting traffic easily as much as we want. Thus, we can generate long-run stress test scenarios by mixing DMA tests and the traffic profile tests. All of those test scenarios can be run in a simulation and emulation environment without any modifications and show the same result. The figure 16 performance result based on simulation time. In addition, the current PSS environment is highly reusable because all the configuration of the test chip platform are parameterized in case that the numbers of the CPU cluster are increased and decreased in the next project. New PSS environment can be created by just modifying the corresponding configuration tables, and the same set of the test scenarios can be validated in a few days. Therefore, the overall productivity highly increased using PSS produced reusability and the automation. Number 4. The lessons learned and a future enhancement. This paper shows how PSS can be used to generate test scenarios for measuring performance of new design methodology as well as test scenarios for system validation in post-silicon. By modeling them using PSS, we can automate test scenarios generation and reduce the code generation efforts significantly. This gives us more time to focus on defining the additional test scenarios which have not been thought of before. Also, PSS provides the randomization of the attribute in generating new tests and support the composition of the new scenarios by leveraging existing actions so that we can compose interesting test scenarios quickly. It leads to improve the quality of the post-silicon validation. The acknowledgement. The authors would like to acknowledge the contribution made by Cadence for developing the CPU benchmark test and the traffic profile generator required for our project. References. And okay, thank you. Thank you for your time. As today I led post-silicon performance validation using PSS from the DVCon conference. Thank you.